students, today I'll discuss the topic factors affecting crystal field splitting. Okay, before going to these factors, we should know what is a crystal field splitting. Already we have discussed this topic. So whenever there is a central metal atom, if this is attacked by any ligand, so ligand also have some electrons in it, and valence electrons also consists of electrons. So both the electrons gets repulsions. Because of this repulsions, the d orbitals, 5d orbitals which are having equal energy will get splits into two sets. Okay, they are Eg and T2g sets. Okay, so this splitting is called as a crystal field splitting. This splitting can be affected by different factors, that is the nature of ligand, oxidation state of the metal atom, size of the d orbitals, and geometry of the complex. So let us discuss the nature of the ligand first. So the ligand which have a large negative size, negative charge and small size will have more crystal field splitting. Why? Because the one which is having more negative charge will have more electron density on it. So if it is having more electron density, what it will do? This electron density and electron density in the valence shell gets more repulsions. Because of this repulsions, the splitting will become more. Okay, the strength of the ligand will be given through a spectrochemical series. Okay, so you can see this spectrochemical series, the decreasing order of the ligands arranged in this series. Okay, you can see CO carbonyl group, CO carbon monoxide group, CN cyanide, NO2 minus nitro group, ethylene diamine, and H3 pyridine group, H2O water, oxalate, fluoride, chloride, bromide, and iodide. Okay, the ligands which are at the edge, they are weak field ligands, they'll produce less splitting, and the ligands which are at the top, they are strong field ligands. Okay, strong field ligands will give the more splitting. They'll make the electrons to pair up. Okay, and these weak field ligands will not make the electrons to pair up. Okay, we can give the best example. And this spectrochemical series will helps to predict the paramagnetic behavior of the complex. Already we know what is a paramagnetic substance. The magnetic substance which consists of unpaired electrons will be a paramagnetic substance. So I'm giving these two examples. You can see here. So iron is having two complexes. One is aqua complex, another is cyano complex. In this aqua complex, the oxidation state is +3. And in this complex also, if you calculate the oxidation state, you will get +3. Okay, so +3 means we are having iron atomic number 26. If I write the electronic valence configuration, 3d6 4s2. Okay, if I remove 3 electrons, it will become 3d5. Okay, 3d5 means I can write like this. Okay, now we are having 6 aqua ligands. So 6 aqua ligands donate 6 pairs. So we won't pair this ligands because water is not a strong ligand, it is a weak ligand in this series. So what we will do, we will not do pair up of this electrons. So next orbitals will be vacant to donate the electrons by this aqua ligand. So 6 aqua ligands donate 6 pairs. So 4s, 4p and 4d. So 1s orbital, 3p orbitals and 2d orbitals involving in this structure formation. So it is sp3 due to hybridization. Okay, and you can see if you are calculating a spin only formula, if you want to calculate the paramagnetic nature or diamagnetic nature, magnetic momentum of the complex, you need to give the formula mu s equals to root over n into n plus 2. So 5 unpaired electrons are present, 5 into 5 plus 2, and 5 into 7 it is 35. So I am getting 5.92 Bohr magnetons. And it is also called as high spin complex. Why? Because more unpaired electrons are present. That is the reason we will call this as a high spin complex. Okay, next coming to the next structure. If you observe this one again, same atomic number of iron is 3d6 4s2 and Fe plus 3. And Fe plus 3 I remove 3 electrons. So I'll get 3d5. So 5 electrons in 3d I filled. So what will happen? It is a Cn is a strong ligand. So it will pair up the electrons. So 5 electrons will be paired, 2 pairs and 1 unpaired electron. So what will happen? So the remaining ligands donates the electrons to the inner d orbitals. So 3d, 4s and 4p. So d to sp3 hybridization. Okay, this is inner orbital complex. It is outer orbital complex because outer orbitals are involved in the bonding. Here inner orbitals n-1d orbitals are involved in the bonding. So it is a inner orbital complex and hybridization d to sp3. If you are calculating spin, one unpaired electron is present, root over 1 into 1 plus 2. So you are getting root 3 1.724 magnetons. Okay, it is a low spin complex because it is having one unpaired electron. So by this we can predict, so through spectrochemical series, the arrangement of ligands in the in the decreasing order of their strengths is called spectrochemical series. By the help of spectrochemical series, we can identify whether a substance is paramagnetic or diamagnetic. So this is a use of spectrochemical series. Coming to the next factor, oxidation state of the metal. Okay, so if the oxidation state of the metal increases, crystal field splitting also increases. This is mainly because the charge. Okay, when there is a less charge, it won't attract electrons easily. But when there is a more charge, it is ready to attract the valence electrons and ligand electrons also. So when it attracts the ligand electrons easily, the ligand electrons comes and causes repulsions, which leads to the splitting in the valence orbitals. Okay, so more charge causes more splitting. Okay, next coming to size of d orbitals. So when there is a size increases in case of d orbitals, the splitting also increases. This is because when there is a more size, it occupies the electrons easily, ligand electrons easily it occupies. So whenever it occupies ligand electrons easily, the ligand electrons can able to cause the splitting in the d orbitals. So with the increase in the d orbital size, there is an increase in the splitting. Okay. Next coming to geometry. Geometry of the complex. Geometry is nothing but shape of the complex. Already we have discussed different types of complexes: octahedral, tetrahedral, square planar complexes. So in case of octahedral complex, there are a number of 6 ligands will be present. In case of tetrahedral complex, 4 ligands will be present. That means coordination number in octahedral complex is 6. In coordination number in tetrahedral complex is 4. That means crystal field splitting in case of octahedral complex is more when compared to tetrahedral complex. By seeing this relation, we can understand. Okay, so already we know that delta naught, the delta O octahedral splitting is double the value of tetrahedral splitting. This is because the number of ligands present in the shape of the complex. So in the structure of the complex, we can observe the number of ligands easily. So because of more number of ligands, more repulsions will take place, which leads to the splitting easily. So as the number of ligands in a complex increases, that leads to more crystal field splitting. That means it mainly depends on the geometry of the complex. So this is mainly about factors affecting crystal field splitting. Coming to the next topic, crystal field stabilization energy. It is indicated by CFSE. Okay, this energy is the difference between the energy of degenerate orbitals. Okay, we know that degenerate orbitals will have similar energy. So all d orbitals will have some energy in the beginning. So after splitting, they'll have different sets, T2G and EG. So these two sets will have different energy. And the energy difference between these two is called as a crystal field stabilization energy. Okay, the difference in energy between the energy of all the degenerate orbitals and the energy of d orbitals after crystal field splitting is called CFSE. So if you are taking octahedral complex, according to CFT, in octahedral complex all ligands approaches along the axis. Okay, so while approaching along the axis, there is a splitting takes place. Okay, so on the axis we know EG orbitals are present. EG orbitals means dx square y square and dz square. Okay, between the axis T2G orbitals are present. They'll have their dxy, dyz and dzx. So orbitals present along the axis will get more repulsions and more energy. Orbitals between the axis will get less repulsions and less energy. So T2G set is lowered by energy, that is 4 dq. Okay, that's why we indicate with the minus 4. Okay, EG set will rise by energy, that is 6 times, that is 6 dq plus 6 dq will write. Okay, so if we are considering one ion that is having d power p plus q ion. So this if this ion consists of p electrons in T2G and q electrons in EG. Each electron increases or decreases energy by p times or q times. So now you can see gain in energy due to q electrons in EG orbitals. Okay, q electrons in EG orbital. So 6 dq for EG orbital, 6 dq into q. Okay, for example, in T2G orbital, p electrons are present, minus 4 dq into p. Okay, so I'll add total net change minus 4p plus 6q. okay, into dq. This total net change is called as a crystal field stabilization energy. So this is about CFSE. Coming to the merits and demerits of crystal field theory. Okay, so merits indicates the advantages and demerits are the disadvantages or drawbacks of the theory. Okay, so merits. So already we have seen this theory explains the geometry of the complexes. Geometry indicates what? The shape or structure of the complex. Mainly it explained about clearly octahedral, tetrahedral, square planar complexes. Okay, and this theory also explains clearly about magnetic properties of the complexes. And it's also successful in explaining the color and spectral properties of different complexes. Already we have seen the explanation of all these properties. Okay. Next, coming to the demerits. So demerits are the drawbacks of this theory. And this theory only explained about d orbitals of central metal, but not explained about s and p orbitals. So already we have seen the d orbitals which are undergoing splitting, that is crystal field splitting, is explained clearly. But how the s and p orbitals inside, how they are getting attacked by the ligands is not explained by this theory. Okay, this is one drawback. And this theory also fails to explain the relative strengths of the ligand. Already we have seen some ligands are weak, some ligands are strong. Why they are weak and strong, it's not clearly explained by this theory. Okay. Next, it is also given no significance about orbitals ligands. Always it describes about the ligands of orbitals of metal, but not included the orbitals of ligand clearly. Okay, it does not explain the pi bonding in the complex. Pi bonding means there is a double bond inside formation, double bond formation in some complexes, but it always explains the sigma bond formation, but not the double bond formation. Okay, this theory also fails to explain why certain ligands causes large splitting than the others. We have seen some ligands are giving more splitting and some ligands are giving only some small splitting in the d orbitals. Why it is causing large and small splittings is not clearly explained by this theory. Okay, these are the merits and demerits of crystal field theory.